So our machine learning project takes a look at what makes a new movie successful. Let's meet the team. Our team is made up of Eleanor, Arushi, Megan, Diana, and Jonathan. First, some introduction and background. We'll start with the basics. So approximately 230 million tickets are sold every year in the United States for movies. In total, the film industry made almost $11.4 billion in 2019 alone, making it highly profitable. Because of this, there's an incentive to understand what makes a movie successful. Let's now look at the problem at hand. So, our goal is to use supervised and unsupervised machine learning models to predict the box office revenue of movies based on the statistics about the movie. So looking at our data source and sort of our data collection process. So we obtained our source from Kaggle, and in total there were 3,000 movies, each movie having 21 original features. The features that we used span a wide range, including budget, genre, original language, popularity, production company, production country, release date, runtime, cast, and the director.
After we determined what our data would be, we then dived into certain methods in order to cleanse our data and pre-process it. So in terms of data cleansing, our team first all the features of the data for a single film. We came to the consensus it would not be pertinent in determining the success of a film as certain features earnestly was beyond our skill level. We then cleansed the data via one-hot encoding and fixing null values. Our data was then ready for pre-processing.
We utilized lasso regression on our data in order to perform feature selection before running any of our algorithms. We used the logistic regression module from sklearn with a penalty of L1 to indicate lasso, and we used a hyperparameter value of C of 0.12 and 0.15. This value of C tells the lasso method whether or not to trust the training data a lot. The output of this method was an array of booleans, with the value of false meaning that lasso shrunk that feature to 0 and it could be eliminated. This will be mentioned in future slides, but we decided to run our linear and polynomial regression models on both reduced feature sets in order to compare the accuracies between the two. In addition to running lasso with pre-selected values of C of 0.12 and 0.15, we also used logistic regression CV in order to cross-validate the hyperparameter of C. This resulted in a C value of 0.11, which resulted in the same feature selection that we had previously done with a C value of 0.12.
After we were able to cleanse and pre-process our data, we implemented our preferred linear regression. Using the linear module, we were able to implement a method and calculate any estimated coefficients, intercept, and R-squared values for both training and testing data. We performed this module on both 4 and 6 features with a C value of 0.12 and C equals 0.15. We ended up getting a higher R-squared value for C equals 0.15 of 0.621.
Here we have graphs visualizing the different features that we have in our data set by the revenue. So what we're trying to determine from our model. So here we can understand why we might have had not great results with linear regression because budget seems to be the only linear-based model, and while other ones look to be maybe quadratic or other shapes. And this helped us determine what methods we were going to try next.
After running the linear regression model, we also ran polynomial regression, and this is another supervised learning model. We noticed after running linear regression that our data might not be linearly correlated. And the purpose of running polynomial regression is to model any nonlinear relationships within our data, as this has the ability to fit a wide range of curvature. We use the make pipeline method in order to combine two methods of polynomial features and linear regression. We again performed this model on both 4 and 6 features with a C value of 0.12 and 0.15. Like linear regression, we ended up getting a higher R-squared value for C equals 0.15 with a final value of 0.646.
We then moved on to try an unsupervised learning model. So from here we went to k-means. The first step we had to determine was to figure out and visualize how many clusters we might end up having. You can see the first two histograms identify the data without removing any outliers and then removing any outliers. You can see by removing outliers, the data stays skewed, and so no clusters were able to visually be determined from looking at the data. But then k-means, we ran the elbow method for k-means, and the elbow value we found in for the number of clusters we should use was k equals 5. So we ran k-means with a cluster value of k equals 5.
Another method that we used on our data was light gradient boosted decision trees. This machine learning technique essentially gives a prediction model in the form of an ensemble of weaker models, and the weak prediction model in this case is decision trees. We use this technique for both regression and classification tasks on our data.
So now that we've discussed the 4 models that we implemented, let's dive into what these results look like. We'll start by comparing linear versus polynomial regression. So as we can see, for both specific models, the C-value of 0.15 performed consistently better. Based on the results of both linear and polynomial regression, one can see similar R-squared values for both of these models, but with the polynomial regression scores being slightly higher. This could be due to slight underfitting when using a linear regression model.
In terms of our k-mean results, we were able to evaluate the silhouette coefficient for each of our n cluster values. We know that k clusters, when k equals 5, that's our most optimal one, but we wanted to try all of them to see if we could get a better silhouette score. All of the silhouette scores are negative, which means it frequently thinks it is assigning values to the wrong cluster. Because the silhouette score is a measure of how similar the data is to the data inside a cluster versus the data outside a cluster. And it can vary from +1, which represents great classification, to -1, which represents bad classification. So you can see we have negative scores, which would then suggest poor classification. Additionally, the proximity of these numbers to 0 suggests that many of the data points may fall on or close to the decision line, since a score of 0 on silhouette means that it was close to the decision line for each of the clusters.
So as mentioned in our methods section, we ran the light gradient boosted decision tree function for regression and classification tasks. Once we obtained the predictions from regression for both testing and training data, we calculated the R-squared value between the actual labels and the predicted labels. The results were a 0.65 R-squared value for training data and a 0.58 R-squared value for testing data. Once we obtained the predictions from the classification algorithm, we calculated the accuracy score between the actual labels and the predicted labels, which just returns a fraction of the correctly classified samples. The correctly classified samples for training was 63%, and for testing it was 20%. This is likely due to extreme overfitting on the training data and the fact that our data has not done well with other types of classification algorithms, such as k-means, most likely due to the fact that we are working with continuous data for labels that cannot be grouped easily.
So let's take a final look at everything. So what we've learned is that the best machine learning model to use was polynomial regression. We saw that our data didn't really fit a linear model, as discussed earlier. Additionally, clustering didn't work on our regression-based data as it was hard to group up all of our information. In the future, if we were to continue forward, perhaps a neural net or obtaining more training data would help us better classify our data. Thank you. Please let us know if you have any questions, and you can see the link below to check out our project.